Hi there and welcome to this tutorial on subatomic particles. So in this tutorial we're going to be having a look at elements, the constituents of elements, relative charge and relative masses, and the models of atomic structure. Elements are made up of atoms. So each element has only one type of atom. So if we're having a look here, we've got nitrogen. Nitrogen involves two atoms of nitrogen that come together to form our gaseous nitrogen, N2. There's only one type of atom in that particular element, and we have the same with chlorine and oxygen. All these three, they're called diatomic. So two atoms to make up one molecule. So like I said, we've got nitrogen, we've got chlorine, and we've got oxygen here. As I said, an element is made up of one type of atom. So we can see we've got oxygen here, it's diatomic, and it's only made up of oxygen atoms, two of them. Each atom consists of subatomic particles. So these are protons, neutrons, and electrons. So protons, quite easy to remember, P for positive. So we've got protons, which are the red ones there. We've got neutrons, which are neutral, and then we've got our electrons, and that's what makes up our atom. And from GCSE you will already know some information about these subatomic particles. So we know that protons have a relative charge of 1 and a relative mass of 1. We know that neutrons are neutrals. They've got a relative charge of 0, but they have got a relative mass of 1. And finally, our electrons, we've got a relative charge of -1, and their mass, it's negligible, but if we're going to be fussy about it, and we're at A level now, 1 over 2000, so really, really small relative mass. You'll notice that each of the subatomic particles has a relative mass and a relative charge, and we use a relative mass because the actual mass of the subatomic particles is really, really small, and we don't want to be dealing with numbers that small, so dealing with ones is much, much easier. Within the subatomic particles, two of those subatomic particle types are in the nucleus, so effectively in the centre. So this is our nucleus here, or this is representing our nucleus, and there we've got our protons and our neutrons. Don't confuse this, of course, with the nucleus of a cell in biology. We often use the same terms to mean slightly different things, but in both cases, we could say, they're inside within the main structure. So we've got our nucleus in the centre. And yep, our protons and our neutrons. So the electrons are not part of the nucleus of the atom. So where are the electrons then? Well, they orbit on the outside. So orbitals, they're found in orbitals on the outside, and they surround the nucleus effectively. These electrons are really interesting. They give elements a lot of their reactive properties. And the idea is that they have different energy levels. So depending on how distant they are from the nucleus, that responds or represents a different energy level. So we've got 1s, that's quite close to the nucleus. As we move away, we've got 2s, 2p, 3s, 3p, and we go further and further away from the nucleus as we get to different energy levels. So you can see it's increasing in energy, and you'll get to study that in a lot more detail later on. You might remember from GCSE that we have different models of the atom that came about at different points in time. So if we're looking at, or if we're thinking about Dalton's model of the atom, they said that all matter is composed of solid, invisible, tiny spheres of atoms, as you have them here, and each element consists of a different type of atom, and only that type. So here we've got what is representing 3 different elements. So we've yellow here, we've only got the yellow type of atom, meaning that this is an element and of course not a compound. So here we're representing 3 different elements. But if we have a look at Thompson's model, that's slightly different. So atoms, Thompson said, consist of negatively charged particles, so the electrons, embedded in a sea of positive charge. So there's my electrons in my sea of the positive charge. And of course, this is also known as the plum pudding model. And then we came to Rutherford's model of the atom. So Rutherford fired positively charged alpha particles through a sheet of gold. And some of the particles passed straight through, whilst others were deflected back, or they were off-centre. They didn't travel through in straight trajectory. And so Rutherford said that atoms must consist of mostly empty space. This was revolutionary at the time, with a cloud of negatively charged electrons surrounding a tiny, densely charged positive core nucleus. And that is a big misconception with atoms. The nucleus in the center is actually very, very small. In the model we were looking at earlier, the nucleus is very large. The protons and the neutrons are taking up a lot of space. We had just a couple of electrons on the outside. The reality is that the nucleus is really very, very, very small and densely charged. And the electrons might comparatively look quite far away. There's quite a lot of empty space. And then we came to Bohr's models. This just built and built and built as they discovered more and more things. So Bohr said that electrons can only exist in shells or orbits at different energy levels. And you can see they're at different energy levels. Some of these electrons are orbiting close and then further and further away as we go out. And they are orbiting around this densely charged nucleus. And the movement, he said the movement of electrons between the energy levels results in the emission or absorbance of electromagnetic radiation. And you've learnt about the electromagnetic spectrum at GCSE. And so we can link all this together later on. And this was later refined to include subshells, which you will study later as well. And we have Chadwick's model of the atom. So Rutherford initially had suggested the existence of another particle within the nucleus. So they knew it was a positively charged nucleus, but they weren't sure what particles were involved in that. So there must have been a particle alongside the protons in the nucleus. And this is what Chadwick was looking at. Because otherwise, of course, the positive protons would very strongly repel each other. So there had to be something there to stop that happening. So it was Chadwick that first discovered neutrons.